All right, so let's do a warm-up problem. Suppose that y equals f of x is a differentiable function. And so whenever you hear the word differentiable function, that says you have a derivative. Another word you sometimes hear is smooth. And you can think of that. That means it's nice. It has tangent lines. It's got derivatives. So it's a good function. And that at the location x equals 3, the line y equals 4x minus 12 is the tangent line to y equals the quantity of f of x squared plus x times f of x minus 2x plus 2. Determine the possible tangent line, or possibly there's maybe many candidate lines, to just the original function y equals f of x at x equals 3. So when we're looking for tangent lines to a function, really that says I need to know the following. What is f of 3 and what is f prime of 3? Because essentially there should be this sort of duality. If I know a tangent line at a location, I know the information about the function and the derivative. And vice versa. If I know information about the function and the derivative, I know the tangent line. So we sort of have a goal, which is to say, what can we say about f of 3 and f prime of 3? Now, to figure that out, we probably should say, all right, we know something about this tangent line. Now, what do we have? Well, this is the tangent line to this part here. We'll call this, let's maybe call this a name temporarily. We'll call this g of x. It's a different function. And what do we know? Well, so we can say something about g of 3 and g prime of 3. This is like free information for us. The reason I say free information is we have our tangent line. So to figure out what the function does at 3, the question is, what does the tangent line do at 3? And the answer is, what do you get? You get 0. So we're getting that g of 3 equals 0. And now if I want to say, well, what does the derivative of the function do at 3? Well, the answer is, what is the tangent line doing? Well, of course, the derivative of a tangent line turns out to be the slope. So you can say, well, the derivatives match, but we can also often say the slope of the tangent line is the derivative. So what is g prime of 3? 4. So what we want to do is we want to translate this information about g down to information about f. And once we have our information for f, life is good. All right. Well, let's start the translation. So we have, plugging in 3, f of 3 squared plus 3 times f of 3, then minus 6 plus 2 equals 0. Or we could say that f of 3 squared plus 3 times f of 3 minus 4 equals 0. All right, well, what can we do here? It may not be so clear. Let's suppose we call f of 3 some unknown value. Let's call it a. Suppose you saw a squared plus 3a minus 4 equals 0. What would be your response? Yeah, you try to factor, right? But the thing is, these are really the same types of problems. All that we're doing is we're saying, oh, let's just give something a simpler name. So the ability to recognize, this is a quadratic I'm trying to solve, that will show up very frequently as we go forward. So does this factor? I hope so. Otherwise, I've made some poor choices in setting this problem up. So does it?
4.
Sorry, what?
A plus 4.
A plus 4. A minus 1. That's a candidate. Let's check. A squared minus 4a. Minus a plus 4a. Okay, good. 3a. And then minus 4. Good. All right. So the conclusion is a is negative 4 or a is 1. Now, we don't know which one it is. We may be able to figure it out later on. But okay, so we know something about f of 3. So because remember, the f of 3 was the same. So f of 3 is either negative 4 or f of 3 is positive 1. All right. So we know something about f of 3 now. And we used information about g of 3 equals 0. So the next thing is to say, well, what about g prime of 3? So we better say, all right, what is g prime of 3? So let's take g prime of x. Now, How do you take the derivative of f of x squared? Well, we can use the product rule. It's f of x times f of x. Now you're probably saying, isn't there a better rule? And the answer is, there is a better rule. We just don't know it yet. But we will. We'll learn it. We're going to learn all the good rules. But right now we can use the product rule. So the derivative of f of x times f of x, what would that be? F prime of x times f of x, derivative of the first times the second, plus f of x, f prime of x. The first times the derivative of the second. All right. Go to the next term. Derivative of x times f of x. Well, what rule?
Product.
It's a product rule. So derivative of x is 1 times f of x plus x times the derivative of f of x. That's f prime of x. Derivative of minus 2x, minus 2. And the derivative of plus 2, 0. All right. So what do we know? Well, we know that g prime of 3 equals 4. So we're going to plug in x equals 3 and see what we get. So x equals 3. G prime of 3 is 4. Now that's going to equal, here I have f prime of x and f of x. These are actually the same. So I can say that's 2 times, I'll say f of 3, f prime of 3. Then I'm going to get plus f of 3 plus 3 times f prime of 3 and minus 2. All right. Well, we have to explore. Now, the reason I say we have to explore is there's really two possibilities, because there's two outcomes that were possible. If f of 3 were negative 4, this would become 4 would equal negative 8 f prime of 3 plus negative 4, which is f of 3, plus 3 f prime of 3 minus 2. So let's see, minus 4, minus 2, that's a minus 6. Bring it across, that'll become a plus 10. Minus 8 plus 3 is minus 5. So what does that say about f prime of 3? Equals negative 2. Okay, so that's one option. The other option, maybe f of 3 equals 1. So we would get 4 is equal to 2 times 1, which is 2, times f prime of 3, plus 1, plus 3 f prime of 3, minus 2. Well, plus 1 minus 2, that's a minus 1. I can add that across, and I can get 5 is equal to 2 plus 3, 5 f prime of 3. So 5 equals f prime, 5 equals 5 f prime of 3. So what does that say about f prime of 3? It would be 1 in that case. So it turns out that there are two possible lines. Now, I want to be really careful here. And here's what I mean by be careful. I'm not saying that the function f of x has two tangent lines that are different at the same point. Because if I have a function, there's always just a single line. What I'm saying is that if I have a tangent line at this point, it has to be one of these two. And I do know I'm going to have a tangent line because I know that my function is nice. It's a differentiable function. So what are my two lines? Well, if I go with the first option here, I would say the slope is negative 2, y value is negative 4. So y minus the y value is equal to the slope, x minus the x value, and we're at x equals 3. And if you wanted to, you could rewrite this. This becomes y equals minus 2x minus, let's see, this would be plus 6, so minus 2x plus 2. All right, if you rearrange. Or you can come down and do the other option. So y minus your y value, f of 3, is equal to your slope, f prime of 3, times x minus your x value. And this can be rearranged. Y is equal to x, and then this would be minus 3 plus 1 minus 2. So it's one of these two lines. That's tangent. And without more information, we can't go any further. All right, so there we go. There we go. Nice warm-up problem. All right, well, where are we at? What we're doing right now is we're saying, limits are nice, but not limits is nicer. So our goal is to develop this nice set of rules, a collection of rules which makes our life easier. So we want to come up with a set of rules that we can basically say, look, I can take a derivative of any function that we might come across by doing a certain combination of rules. Now I have to have enough rules so that I can handle any function we come across. So the rules take two different types of forms. You'll see here there's sort of a color coding going on. The first type, which is the top, what we have are these are our functions. So in other words, there's a few basic building blocks that we have. So right now we can handle things like constants, x to a power, and e to the x. That's what we talked about before. Now the second type of rule, and that's what you see in the bottom side, these are saying, how do you combine? So in other words, I have my little pieces, but how do I put them together? So you can think of it as if you've ever played with Lego. These are your little bricks. Now, how do you make it look nice? Follow the instructions. And make sure you follow the instructions, otherwise it's not going to look like what's on the box. And that's what you want. Now, if we learn these rules, and you do, you want to learn them, and it comes with practice, then we're going to be able to handle anything that we have. Now, there's still more rules to come, so that's part of today, is we're going to learn a few more rules today. So let's add our next rule. It's called the reciprocal rule, and it says the following. Suppose I want to take the derivative of 1 over a function. So 1 over g of x. Well, the claim is this is negative g prime of x over g of x squared. So, how do we prove it? Well, we follow the rules. And we say, all right, if I want to take the derivative of 1 over g of x, that's the limit as h goes to 0, 1 over g of x plus h minus 1 over g of x all over h. Now, the next step says, okay, let's add the fractions in the numerator and simplify. So you get g of x minus g of x plus h all over h times g of x plus h times g of x. So this right here, this step, this is algebra. You add fractions, common denominators, that type of thing. And once you have it in this form, you're basically done, because you say, all right, I see a couple of things. Normally I'd want g of x plus h minus g of x, so I'll put a minus to put them back in the order I prefer. Then there's this g of x plus h, g of x downstairs. I'll put them on the end. And then we see, aha, we get the minus, we get the g prime of x, and then over here we get the g of x squared. And there's the result. So there's the reciprocal rule. So, let's try a problem. Let's find the derivative of x squared plus 2x plus 2 times e to the negative x. Now, it says there's a first step. The first step we need to do is, what's the derivative of e to the negative x? Because we actually haven't found that yet. So let's talk about that first step. So how can we think of the derivative of e to the negative x? Or maybe a better way is, how can I think of e to the negative x? What's another way to write that? Yeah, 1 over e to the x. So when you see a negative in the exponent, it's like a 1 over thing going on. So this is the derivative of 1 over e to the x. Well, what rule can we apply? The reciprocal rule. You know, we just learned it. We can use it. So it's 1 over e to the x. So according to the rule, it's negative the derivative of the bottom term. Oh, the derivative of e to the x? E to the x. Divide that by the square of the bottom term. Now, if you look at that, you say, hey, I can simplify that, because you can simplify that. What happens? You can cancel off a single e to the x. Then you end up with a negative 1 over e to the x, also known as negative e to the negative x. That's kind of nice. You know, last time we talked about the derivative of e to the 2x was 2e to the 2x, and today we learned that the derivative of e to the negative x is a negative e to the negative x. You know, there's something nice going on here. There's something beautiful. I'm sure we're going to see this again. You know, math, of course there's something beautiful. It's math. Everything's beautiful in math. All right. So now we're ready. Okay. So we now know how to handle the derivative of e to the negative x. Now, how do you take the derivative of this whole expression? What's our big rule? Product rule. So f prime of x, we can say the derivative of the first term, derivative of x squared plus 2x plus 2. 2x plus 2 multiplied by the second one, plus, now leave the first function alone, x squared plus 2x plus 2, and now multiply by the derivative of e to the negative x, which is negative e to the negative x. All right. I think we can go further. Let's simplify this. So what's our next step if we want to simplify? Okay, so there's two things we can do, and they're both fine. One person has suggested, hey, why don't we distribute? All right, that could work. Is there anything else we can do? I'll put a little star here as though to indicate there might be something else we can do. We can actually factor out a common term. What's common to both of these? E to the negative x. Now, which one's the correct one? The answer is they're both correct. Which one do you do? The one that you're least likely to make a mistake on. So our goal is, you know, if we're going to make mistakes, let's make as few as possible. Fewer, the better. All right, so we'll start with the distributing. You'll get the same answer either way. So we're going to multiply this through. We're going to multiply that through. So we get 2x e to the negative x plus 2 e to the negative x. And here, don't forget the minus. Minus x squared e to the negative x minus 2x e to the negative x minus 2e to the negative x. All right. Well, I think something nice should happen. Does anything nice happen? Yeah, what's happening? 2x e to the negative x minus 2x e to the negative x. 2e to the negative x minus 2e to the negative x. Minus x, oh wait, no, there's nothing else left. Okay, so that means we end up with a rather very simple expression. So it can be the case that you might start with the derivative of a function that looks really big, but when you take the derivative and you simplify, it collapses to something very small. Of course, sometimes it feels like the opposite is true. You might start with a function that looks really small, and you take the derivative, it's like, it's going to get huge. But, well, all right, it's got to be balanced. Okay, so the next rule is actually very much like the reciprocal rule. It's the quotient rule. And students love the quotient rule for some reason. They're like, I'm always going to use the quotient rule. It's okay. It's a nice enough rule. There are better rules. So the derivative of f of x over g of x. So how does that go? Well, it's f prime of x g of x minus f of x g prime of x divided by g of x squared. Now the thing that makes this hard is the fact that there's a minus in the middle. You see, for the product rule, you always have that, it's like f prime times g plus f times g prime. And as you say, I don't remember which one comes first, you're like, it's okay, it's all plus, everything's great. But for the quotient rule, the minus really matters. Now, if you forget, you're off by a sign, 1 point, sure. But you know what? We want all the points. So just be careful. How do you remember? Some people, they have sort of this rhyme, low d high minus high d low. If that helps you remember, that's fine. That's fine. But whatever you need. All right, now, I already said that. Okay, so how are we going to prove this? You're probably like, he's going to pull out another limit. No. Why do limits when we don't have to? Here's the beautiful thing, is a lot of these rules combine together. And in fact, once we have a bigger collection of rules, we can actually take some of the rules we've already written down and say, we actually don't need all of these. It turns out that the quotient rule is a combination of the reciprocal rule and the product rule. So I can think of f of x over g of x as f of x times 1 over g of x. I mean, that's certainly true. That's a true statement. Now what's happening is I'm taking the derivative of two things multiplying together. So, product rule, take the derivative of the first times the second. Okay, so f prime of x times 1 over g of x. Then add the first, f of x, times the derivative of the second. So that's the quotient rule, negative g prime of x over g of x squared. Now the last thing is we'd like to add these together. So if I want to add these two things together, what do I need? Common denominator. You'll compare the denominators. The first term has g of x. The second term has g of x squared. So what's the common denominator? G of x squared. So what I need to do is I have to come to the first term. I'm going to multiply it by g of x over g of x. And if you do that, you'll see you'll get f prime of x times g of x. The second term, the minus f of x g prime of x, and then the common denominator g of x squared. So there's the quotient rule. All right, good. Well, let's try a problem. Here we go. Find the derivative of the following. The square root of x plus x squared all over 3x cubed plus x e to the x. Now we're like, yes, we're finally getting to do the good ones. Okay, so how do we begin? What's sort of the big rule? First layer, what's our rule that we need? Quotient rule. Okay, quotient rule says you take, low d high, if you go by that. So you can say, take the bottom, 3x cubed plus x e to the x times the derivative of the top. Now, square root of x, that's nice, but it's not very calculus-y. How do you make it a bit more calculus-y? X to the 1/2. Okay, so the derivative of x to the 1/2 plus x squared, what would that be?
X over, or
yeah.
x over times x.
Well, so the way I would do it, if I follow the rule here for x to 1/2, bring the exponent down 1/2, and then it'll be x to what power? Negative 1/2. And just follow the rule for right now and then clean up later. All right. Plus, derivative of x squared? 2x. All right. Bottom times the derivative of the top minus, now it's the top, square root of x plus x squared, times the derivative of the bottom. The derivative of 3x cubed? 9x squared. And now we come to the derivative of x e to the x. How do you take the derivative of x e to the x? Sorry, what? Yeah, it's a product rule. So, derivative of x e to the x. Okay, derivative of the first, that's 1. So 1 times e to the x plus x, and the derivative of e to the x? E to the x. All right. All over 3x cubed plus x e to the x, the bottom term, squared. All right. Now, after we've gone to this stage, what's the next step? The next thing to do is box the answer. Because that's the answer. It is the derivative. Now you might be thinking, wait a second, hold on now. You didn't simplify. We weren't asked to simplify. So here's the thing. This calculus class is not a simplified class. And I know your high school teachers whom you dearly loved. You're like, I loved going to my math class when I was in high school. And the teacher told us that when you get to college, you're going to have to simplify. But no, you don't. Not always. Occasionally we might. If we ask you to simplify, it's because the answer truly is simple, and we just want you to enjoy the beauty that is math. But a lot of the times you don't need to simplify, and you don't gain anything by simplifying, other than by gaining the chance of making more mistakes. So if we don't have to simplify, we shouldn't. Now, when do you simplify? Generally, the 2 times you simplify are 1, if it tells you to. That's a pretty good sign to simplify. And 2, if you have to use this in another step of a computation. But if it's the last part of your computation, then we're just happy with leaving it as is. Now, I will say that there's a tendency to look at these types of problems. And initially, you might look at this and you say, okay, this is what I see. The derivative of lots of stuff. And it's not so clear. One of the hardest things that has to be done, what you have to figure out is to say, what am I doing? What tool am I applying? So I like to think of these problems as having layers. I like to say they're like onions. Onions have layers. Derivatives have layers. And they're also, derivatives are like onions because we're going to cry a couple of tears perhaps. But the point is, think about what's going on. So when you look at a problem like the problem we just looked at, there's actually a tremendous amount of layering going on. So if you look here, it's a little bit hard to see, but you'll see here there's a series of boxes within boxes within boxes. Each box that you see is a rule. And you can, if you look and you count, I think there's about 10 different boxes, which means that when you took this one derivative, you pulled out 10 different rules. Now you might think, really? Did I do that many different rules? Let's talk about what the rules were. So what was the big rule? Sort of the outermost layer. The quotient rule. See, that's the big box. It says, I have the quotient rule. Then you said, all right, the upstairs. Now notice there's a box here because you have this addition going on. What rule do you use when you have addition? The sum rule. That says if I have a derivative of 2 pieces, I can take them individually. How about the derivatives of square root of x or x squared? What rule are you using there? The power of x to the k. And each one of them had its own application of the rule. Downstairs, when we had to take that derivative, again, there was an addition. That's a sum rule. Notice that you had the 3x cubed. There is actually a rule that you use there. Do you remember what rule that is? We don't give it. There's like a constant rule. Sometimes it's called the constant multiple rule. But it's one of those rules that we use so often, we don't even think about it. It says, hey, if I'm taking the derivative, pull the constant out. So there was a rule that came in. Then x cubed, again, that's a power rule. How about taking the derivative of x e to the x? Product rule. And then you say, okay, then for each one of those, you have a power rule, the derivative of x, then you have the derivative of e to the x. So what you have is lots and lots of things being stitched together. Now, how do you take your derivatives? The answer is just work through one layer at a time. Don't be overwhelmed. Just think about, okay, what's the rule I'm using right now? And just be patient. Derivatives become very mechanical. And if you just follow the rules, you'll be okay. And it comes with practice. And don't worry, we're going to give you practice. You get homework problems, you get quiz problems, and the best of all, the exam problems. Practice, practice, practice. All right. So, the other thing I want to talk about today is higher order derivatives. So in other words, we've taken a derivative once. Well, why stop there? let's keep going. So maybe we want to take more derivatives. So if you think about one of the pictures we had before, is you can think about, we have this machine. So in this machine, this particular machine looks something vaguely like this. It's called the derivative machine. And what happens is you put into this machine a function, f of x, and out comes this new function called f prime of x. So we call this the derivative operator. So, but we say, okay, the derivative says start with a function, I'll make a new function called f prime. But now you have a new function. What do? Well, you can say, let me do that one more time. I'll put f prime back into the machine. So you're saying, hey, let's plug this f prime back into the machine. If you do, you'll get a new output called f double prime. So it's like you're repeating the derivative. It's the derivative of the derivative. I need to come up with a better set of colors. That right. So you plug f in, out comes f double prime. And of course you can repeat over and over again. So what's happening? Well, when you take the derivative of the derivative, you're really saying, how is the derivative changing? So you start with your function, y equals f of x. The first derivative, we talked about a couple ways you can write it, y prime, or f prime, or dy dx. The second derivative, well, y double prime, or f double prime, or if you like the d notation, and there's a lot going for the d notation, d squared y over dx squared. Now you might think, that doesn't seem right. Why is it that in the numerator the d gets squared, but in the denominator the x is getting squared? We actually can talk about that, and there's good reason for that. So here's sort of an example way to think about it. So if I want to think about the derivative of y, so if I start with y, and I say take its derivative, I write d dx. So that says take the derivative with respect to x. If I want the second derivative, it says, hey, take the derivative of the derivative. So you can think about what's happening. What's happening is you're applying this twice. So if you think about it in that way, it's like, okay, it's like this d dx thing, that's what's being applied twice. So you can think of it, once you see that, it's like, okay, d squared dx squared. So that's not unreasonable. But there's also some benefits to thinking of it this way. We'll get to that in just a few minutes. Now, the nth derivative, we change our notation. So instead of putting lots of primes, we put y and then an exponent, parenthesis and parenthesis. The parenthesis says, hey, this is a derivative. I'm not raising it to the nth power. So this is d to the ny over dx to the n. Again, f and a parenthesis n of x, nth derivative. Now, why do we go to this notation? Well, because you can imagine maybe you're taking, say, a 17th derivative. And if you're having to write down a 17th derivative, you might say, is that really 17 primes there? Maybe. I don't know. But if you write 17, it's like, yep, 17th derivative. I see it. And so it's a convenient notation. And you might be thinking, wait a second, are you telling me that at some point in the future I'm going to have to take 17 derivatives? I'll make it even better news than that. When you get to Calc 2, oh, good times coming in Calc 2, and you get to the very end of Calc 2, you're not just going to be taking 17 derivatives. You're going to take all the derivatives, infinitely many, and you're going to do it all at once. It's going to be beautiful. You have something to look forward to when you get to Calc 2. So these are essentially the important ideas. You can take derivatives of derivatives, and we have notation to handle that. But there's something else that's nice, and I want to talk about, and that's the units of the derivative. And this really helps shed insight into why this notation makes some sense. So suppose I have y equals f of x. Now that says, okay, I put something x into my function f, I get some output y. So for helping us understand things, or sort of giving us a motivation of what's going on, I'm going to try to use an example that you're comfortable with. So I'm going to say, let's suppose x is a time in seconds, and let's suppose y is a distance in meters. So I have seconds, then I have meters. So I can think then if my function is saying, hey, that's like position, because I want to know a location, which is a meters kind of thing, at a given time. So let's think of that as our function. If you think about what is dy dx, well, it's this limit as z goes to x of f of z minus f of x over z minus x. But if you look, the numerator says that's the difference in your output. The denominator, that's the difference in your input. So what you end up with is you'll end up with the units of y over a units of x. So if we go back to our example, if y was meters and x was seconds, the derivative would be meters per second. Okay? Change in y over change in x. So that says if my function was position, the derivative becomes velocity, meters per second. Okay, what about second derivative? The second derivative is the derivative of the first derivative. So by the definition, that's f prime of z minus f prime of x over z minus x. So, again, it's the units of f prime of x over the units of x. And if you work it out, you get the units of y over the units of x squared. So if you go back again, so I'm taking one derivative, I got velocity. I take the second derivative, the units would be meters per second squared. That's acceleration. So the derivative of velocity is acceleration. That's meters per second squared. Now you probably think, why in the world do I have a second squared? I've never seen a square second. And it's not that's a second squared, but it's meters per second, and that the units combine. And in general, this is why I like the notation. And some people really like this notation. You know, I like it, but some people are like, I really like the notation. So if you look at the nth derivative, you say, okay, what are the units of the nth derivative of y with respect to x? Notice the y only has 1. So if you look at that, it's just the single units of y. But the x downstairs, that has an nth. So it's the units of x raised to the nth power. And that's going to be true for any set of units that we use. So we could make up crazy things. So there was an exam problem last year where there were things like flurbles and blargs. And you had to figure out what was going on. And people were like, flurbles and blargs, I have no idea what these are. And the point is you don't have to know what they are. You have to just understand how units work. And so, good times. All right. So let's do a few more examples. Higher order derivatives. All right. So, find the fourth derivative of the function f when the function is t squared e to the t plus t to the fourth plus 11t cubed minus square root of t plus 317. All right. Well, let's have fun. See you on the other side. No. Come on. It can't be that bad, right? Okay, so let's go through our rules. How do you take the derivative of t squared e to the t? Product rule. So derivative of the first times the second plus the first times the derivative of the second. Derivative of t to the fourth? 4t cubed. All right. Derivative of 11t cubed? 33t squared. Okay, square root of t, well, we need to update that. Square root of t is going to become t to the 1/2. So the derivative will be minus 1/2 t to the negative 1/2. And the derivative of 317? 0. It's constant. All right, this one's not so bad. Okay, 1 down, 3 to go. F double prime of t. All right. How do you take the derivative of 2t e to the t? Product rule. I can think of my two pieces as 2t and e to the t. So the derivative of the first times the second plus the first times the derivative of the second. Now comes the t squared e to the t, be another product rule. Derivative of the first times the second plus the first times the derivative of the second. What's the derivative of 4t cubed? 12t squared. What's the derivative of 33t squared? 66t. And the derivative of minus 1/2 t to the minus 1/2? It'll be plus 1/4 because it's a minus minus. And then it'll be t to what power? Negative 3 over 2. All right. Now, is there anything we should do here? We can combine some things. It turns out that these two are really similar. In fact, they're the same. You might think, hey, that's cool. I wonder if that's a coincidence. And the answer is, no, it's not a coincidence. And how do I know that? It's on the quiz. There's something beautiful that goes on. So, okay, you can combine those two together into 4t e to the t. All right, you ready for the next round? Yeah. Third derivative. So, derivative of 2e to the t, that's easy, 2e to the t. Derivative of 4t e to the t, well, derivative of the first, which is 4, e to the t, plus 4t times the derivative of e to the t, which is e to the t, plus, now come to t squared e to the t, product rule. You get derivative of the first, 2t e to the t, plus t squared times the derivative of e to the t. All right, good. Plus the next one, derivative of 12t squared, 24t. Derivative of 66t, 66. And the last part, 1/4 t to the negative 3/2 will be minus 3/8 t to the negative 5/2. All right. We're making it. Only one to go. Should we do anything before we take our next derivative? Yeah, we can combine a couple of these. There's 6e to the t, and there's 6 times t e to the t. That'll help simplify things. All right, good. Now we're ready for our last derivative. All right, here we go. The fourth derivative. The final derivative that we have to take. Derivative of 6e to the t? 6e to the t. For the derivative of 6t e to the t, it's a product rule, so I'm going to do that again a little bit sped up. Derivative of 6t is 6 times e to the t, plus 6t times the derivative of e to the t, which is e to the t. T squared e to the t, that's a product rule. So derivative of the first would be 2t times e to the t, plus t squared times the derivative of e to the t, which is e to the t. All right, go to the next term. 24t, what will that be? 24. The next term? 0. Nice. The last one. 15/16 t to the negative 7/2. If we wanted to, again, we can combine some terms to the 12e to the t. Here you get 8 times t e to the t. But we don't have to. Why? Because we've got to our fourth derivative. There we go. Now, what did we learn? Well, we learned that you're amazingly patient and willing to watch me take 4 derivatives. But, the point is, be patient. There are 2 things I want to point out. What happened to this 11t cubed? Where is it in the final answer? It's gone. Now why? Well, I can ask the same thing about the 317. What happened to it? Well, we say, 317, you take a derivative, it goes away. So what happened to the t cubed? When you take enough derivatives, what happens? It gets to a constant, then the derivative goes away. So in fact, if I'm taking a derivative, if I have a nice whole number and it's smaller than the derivative I take, it's going to disappear. Now what about t to the fourth? Now that actually does show up. Where does it show up? That was the 24. So in that case, what happens is you'll notice every derivative you have like a t to a number, you're knocking the power down by 1. So if I started with t to the fourth, by the time I hit the fourth derivative, I'm going to be down to t to the 0, which is a constant. So I can play with that. And so I can actually predict what happens. Now where does the 24 come from? That's 4 times 3 times 2 times 1. Every time you take a derivative, the exponent comes down. So with that in mind, why don't we answer the following question? So here we're going to find the derivative at 0 for some certain values. All right, so now our function, different function, g of x equals 2 e to the x plus x to the 8th. So I want to find the 10th derivative at 0. So again, this is g of x equals 2 e to the x plus x to the 8th. What is the 10th derivative at 0? Well, let's start by saying, what's the 10th derivative of x? What's that going to be? Well, let's talk about our two pieces. Let's start with x to the 8th. It's going to be 0. It's the same thing that we talked about. Every time you take a derivative, the exponent drops down. We're taking 10 derivatives, but we're starting out with power x to the 8th. So we're going to wipe that out if we take 10 derivatives. We still have that 2e to the x. So what happens with 2e to the x when I take a derivative? It's 2e to the x. And then if I take another derivative? 2e to the x. How about the next time? 2e to the x. Okay, do you see a pattern? Yeah. You're always going to end up with 2e to the x. So the 10th derivative of this function is 2e to the x. So the 10th derivative at 0 will be 2. Because I can plug in 2 times e to the 0. What if I wanted to find the 8th derivative? Could I do that? Is there still the 2e to the x? That's certainly, I think we can all agree on that. But what's happening to this x to the 8? It's going to become a constant, right? Because if I take 8 derivatives, I'm going to knock one off from the exponent every time. So after 8 steps, I'm to the 0th power, x to the 0. That means I'm to a constant. Which constant? Okay, so some people may have seen this before, but it's 8. That's very exciting. It's like, 8, woo! 8. No, this factorial doesn't mean that we're excited and we're pumped up. It's actually a notation. It's a shorthand for 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. See, every time you take a derivative, the power comes down, the power comes down, the power comes down. Okay, so what does that mean? Well, that says that g 8th derivative at 0 is 40,322. Right? Because 8 factorial is 40,320, then you add 2 more. No, you could leave it as 8 factorial plus 2. That's probably a better way to write it. All right. You don't have to memorize your factorials. What if we went crazy? 100 derivatives. And I say, what's the 100th derivative look like? 2e to the x. So what's happening here? Well, what's happening is you're doing something really nice in mathematics, which is to say, aha, I see a pattern. And if you see a pattern, what you say is, what does the pattern predict in the future? So you can take higher order derivatives by saying, what's the pattern and what's going on? And that's it for today. And we'll pick up again next time.